Thank you. Yeah, so I'm Wen-Ting from the UC Berkeley RISE Lab, and today I'm going to talk about how to enable secure collaborative learning via the use of cryptography so that you can share your data without showing your data. So recently, many organizations are increasingly interested in collaborative learning, where multiple parties jointly compute a model or do inference on everyone's data. And collaborative computation can be very beneficial because it allows organizations to compute on more data, right? So they can train more accurate models, or in some cases compute on more diverse data, right? Maybe geographically diverse data, so that you can create more holistic models as well. So both can create better solutions to the kind of problems that many organizations want to solve. However, there's a dilemma here because the collected data is often sensitive. So on the one hand, right, we have people who want to do collaborative computation, but they require sharing the data. And on the other hand, many of the collected data is sensitive in nature and simply cannot be shown in plain text to other parties. And what you have here is really a huge loss of opportunity here because the kind of applications that can be enabled by sharing data now suddenly you can't compute it anymore, right? Because the data in question is very sensitive. So actually, I'm going to also make it more concrete by presenting two real use cases that we've seen with the companies and the organizations that we collaborate with in the RISE Lab. So first use case is a financial use case, right, where you have a bank here who actually wants to detect fraud using machine learning by training a machine learning model, for example. But the problem here, of course, is that criminals actually conceal their illegal activities, right, their illegal transactions across many banks. So that using just one bank's data is kind of, you can create some kind of model, but it's probably not going to be super accurate, right? So really, if you want to compute an accurate model, ideally what you want to do is to compute this model using data across many banks. But however, this cannot currently happen due to business competition and in some cases possibly regulatory constraints as well. Another real use case that we heard from was flu outbreak prediction actually here. So you have flu outbreaks in California every year. And this medical organization that we talked to, they actually want to distribute vaccines better by actually predicting the locations of outbreaks before they happen. And because these locations are, because this involves kind of location-sensitive data, right? So ideally, what we want to do is to actually compute a flu prediction model using patient data, using geographically diverse patient data from hospitals across California. But again, this currently cannot be done because these hospitals cannot share data due to privacy regulation. Right? So in fact, there are many applications that can be enabled by data sharing. So you have fraud detection, flu prediction. I actually just had a meeting today with someone who is interested in nuclear facility auditing, as well as, for example, cloud-based video analysis for home intrusion. All these applications often cannot happen today, right? Because the data in question, the data that you have to compute on is very sensitive, and people are really unwilling or in some cases unable to share this sensitive data for collaborative computation. So the question that we want to ask is how can we actually solve this problem, right? To allow the organizations to share data for collaboration, but then without actually showing the plain text data to each other. And as it turns out, this setting corresponds exactly to a really well-known research direction in cryptography called secure multiparty computation, or MPC. And as you can see from the references, it was started in the 80s, actually, so it's been around for a while. And the idea for secure multiparty computation is to have the parties emulate this trusted third party via the use of cryptography, but without actually using a trusted third party. So in the trusted third party case, what you would do is to actually give the data to this trusted third party. The third party computes the whatever it's supposed to compute and then gives the result back, right? So in this case, what you're doing instead is to send encrypted data, right, to the parties involved, to all these banks, in this case, involved in the computation, and use this cryptographic technique, right, to use MPC to compute an encrypted result. You decrypt it, and the final result is released in plain text to all the banks, to all the parties. So it's really cool because it has the same exact security guarantees of utilizing an ideal trusted third party, but at the same time, without utilizing such one. So basically, the security guarantee it provides is that no party should learn any party's input beyond what is beyond the final result that is released to all the parties. Right. So in terms of secure collaborative computation, we have or secure collaborative learning, I suppose, we have mainly seen two different paradigms of doing so. And the first one, I think many of you might have heard of, is federated learning. And this second paradigm is actually kind of a term that we coined in the RISE lab. We call it coopetitive learning. And I'll show both what the word means and also what these two paradigms actually entail. So first of all, federated learning, right? So what happens in federated learning is, again, right, you have these data that from across many different organizations, you want to train a model. And the way to do it is you first compute local model, right, from these in this case, these banks using their local data. And then you use secure multi-party computation to securely aggregate these local models into a global model. And then each party actually, so you get a result from this secure aggregation, right? And then each party actually receives the plain text global model from the secure multi-party computation. And then with this model in plain text, right, you can then, what they can do is further refine this global model using their local data again, apply the local updates, and repeat this iterative process, right? So this is federated learning. What we've been working on in the RISE lab, we decided to name it coopetitive learning because the paradigm is a little bit different, and since it's a new word, I decided to provide a dictionary definition here, along with a pronunciation guide, right? I also had some difficulty pronouncing the word in the beginning. So it's a portmanteau between cooperation and competition. And really, we felt like this word describes the setting very well because it's a collaboration between organizations that might possibly be competing with each other in the hope of mutually beneficial results. And in this setting, right, in contrast to federated learning, so what you do is that you can still compute your local models, right, using your local data. But then once you compute that, you use MPC to aggregate the models together. And then actually what we do in coopetitive learning is that MPC will keep the intermediate models encrypted and then give these, the global encrypted model back to the parties. And then the parties actually will update on this encrypted model using cryptography. And then you do this iteratively again, right, using MPC. And actually only the final model is released in plain text to every party. So in this case, the final model is decrypted jointly and then given back to each party. So the two paradigms are somewhat different. And I would say that in terms of comparing the two, possibly for use cases, right? So for federated learning, it is faster because what you're doing is that you're revealing the intermediate global model, right, to the parties in plain text so that they can actually update their own, apply their local updates in plain text as well. So the minus is less secure because it does reveal the intermediate global model. And actually, we have seen some concrete attacks as recent as the IEEE S&P, where I presented my work recently. They actually have some concrete attacks where, because you can see the intermediate global model, if you have an attacker who compromises one of the parties, right, then the attacker can actually try to train something different and try to bias the model to learn about another party's private training data. So yeah, so on the other hand, for coopetitive learning, it is slower than federated learning usually in performance because we're keeping the intermediate global models also private, right, also secret. But it does provide strong security guarantees. And we have, to this day, we haven't seen any concrete attacks on this paradigm. So there has been a bunch of works in both federated learning and coopetitive learning. So here I'm just citing some papers. So on the federated learning side, we have some great papers from Google. Federated learning strategies for improving communication efficiency and practical secure aggregation for privacy-preserving machine learning. On the coopetitive learning paradigm, we have also seen some work from Secure ML, which is a work that uses MPC to train a variety of different models ranging from linear models all the way to neural networks, but making some assumptions there as well. And we have been, in the RISE lab, we have also been working on different work. So I actually recently presented a system called Helen, which is a maliciously secure coopetitive learning for linear models. And this was actually presented last Tuesday at IEEE S&P. We have a system called MC², which is a platform for secure coopetitive learning, which really tries to think about the whole machine learning ecosystem, like how would users actually want to use this in practice. And Delphi, which is under submission, is a cryptography inference service for neural networks. And I'm going to briefly talk about my work on Helen. So going back to the banking use case before, right? So our bank has heard about MPC and is very excited to utilize MPC to compute a fraud detection model with other banks. But it wants to make sure that its desired security properties are satisfied. So from a bank's perspective, what does a bank want, right? The bank wants to trust itself, right? It wants to make sure that its data confidentiality should not depend on the correct behavior of other banks, so that if other banks misbehave, then the data privacy of our bank is still guaranteed, right? And this roughly translates to the following threat model. Might be slightly technical, I don't know. So first of all, we want the secure computation to be executed among all of the parties that are participating, which are just all the banks. We want to allow the attacker to actually be able to compromise P-1 out of the P parties. So a very strong, we give the attacker very strong ability here. We want to have protection against a malicious attacker, so where the attacker can actually deviate from the protocol. So again, this corresponds to the possible misbehavior that you see from other banks, right? We do want to allow the parties to choose input data of their choice, right? So they should be able to choose whatever input data they want to put into the secure computation. And we do want to allow the parties to learn the final model, because this is what they're computing on, right? So if we, under this kind of threat model, if we look at the prior work, actually currently the only framework that handles those requirements is what we call a generic MPC framework. For example, SPIES is one such prior work. But the challenge here is that really the performance, right, that you get. Because actually we tried to implement a stochastic gradient descent for a simple linear model like Lasso using this generic MPC platform. And for 4 parties, 100,000 samples of party, 90 features, we couldn't really run it. We estimated it would take 3 months to actually train a model, and actually ran out of memory way earlier, right? So this is actually assuming unlimited memory that would take 3 months. So in our work, right, we designed and built Helen, which is a training system that is able to give you the guarantees or strong security guarantees I mentioned before, where you have a potentially malicious attacker who can compromise a majority of the parties, right? And we decided to limit our scope a little bit and start with linear models, regularized linear models, which we think still solves a significant slice of machine learning and statistics problems, like cancer research, genomics, financial applications. So basically the use cases that we explored. And as it turns out, improving performance under such a strong threat model is a pretty difficult problem, right? And really in Helen and as part of the RISE lab, what we're good at is to really combine kind of tech insights from different areas, from machine learning systems, as well as cryptography, to design a tailored solution that's very efficient. So with our techniques, I'm not going to dive into the actual techniques, we're able to reduce the estimated 3 months of training to actually just 2.5 hours. That we were able to run it and produce a model with the same accuracy. Okay, so that's like a very brief overview of secure collaborative learning. And I think that, both me and I guess my lab mates, my advisors think that this is a very cool direction, and it can create a lot of value in society because by enabling applications that couldn't be done before. I presented two main paradigms, federated versus coopetitive. I mean, each one has its advantages and disadvantages. So, in order to find the right paradigm for your setting, you should, think carefully about what your application requires. We're actually working on open source MPC platform for coopetitive learning this summer in the lab. So we're really hoping to open source or have a nice, first initial version of the system built by the end of summer and open source it so that other people can use it. And yeah, so I would love to learn about your use cases if you think that this might be useful for your application. And yeah, that's it. Thank you.